Hello, my friends. In this video, we're going to learn what Kepler's three laws of motion are, these laws of planetary motion. And we have already learned in two other videos about the orbits of planets that there are 6 orbital elements, 6 things we can describe about the orbit of a planet, and we take those 6 things and we plug them in. We put them into Kepler's 3 laws of motion, and bingo, presto, magic, out comes the position of the planet. So these are the 3 laws. The first law is not a formula, but a geometry, a statement of how things work, that each planet orbits around the sun in an ellipse. The sun's center is always located at one focus of the orbital ellipse. The sun is at one focus. The planet follows the ellipse in its orbit, meaning that the planet to sun distance is constantly changing as the planet goes around its orbit. This is quoted. That's an exact quote from this nasa.gov website, and they give the exact address. And you can draw an ellipse yourself. Take 2 pins and stick them in a piece of cardboard, for example. Just, 2 pins, stick them in a cardboard. Take a string, and the string is any length longer than the distance between the 2 pins, and take a pen or pencil and then stretch it and draw a shape. And that shape is an ellipse. How cool is that? That's what you do to make the shape of an ellipse. And the closer you put the 2 pins or nails or whatever to each other, the rounder the ellipse will be. So the farther apart you put them, the longer and skinnier the ellipse is, or as you know, if you watch those first 2 videos, what we call the eccentricity, the greater the eccentricity is. And what you'll notice is that when the eccentricity is large, such as in the image being drawn here, look where the sun is. It's way, way almost touching the orbit. So one of these 2 tacks or pins, whatever you want to call them, is the sun. The other one has nothing there. So say the one on the right is the sun. There's nothing where the one on the left is. You have an ellipse, and these 2 points are called the focus points. Plural is foci, or some people pronounce it foci. The 2 foci, or focus points. So let's say we remove, after this person finishes drawing this ellipse, we remove the string and we remove this pin on the left side. We have just the one on the right, and that's the sun. And this would be the orbit of a planet with a high eccentricity. This would be like a comet. This is what comets are like. Comets have extremely high eccentricity, and they get extremely close to the sun and then very far away. So that's what their orbits are like. So a comet, which is very far away from the sun for most of the time, and then comes extremely close to the sun, actually follows the same behavior as the planets do. It's just that it has a higher eccentricity. And, maybe made of different things and whatever, different physical characteristics, that's just another issue. But as far as its orbit goes, it's following Kepler's laws. Doesn't seem like it because the comet is so far away and then comes very close to the sun, but it's exactly what we're seeing here. That's the nature of an ellipse. So as the eccentricity gets greater, the distance between the focus points becomes much, much greater, as we see here. Because actually this ellipse, you can imagine it could be even skinnier. And then, the orbit gets even closer to the sun and even farther away. So, that's how you can actually draw an ellipse. Now, so first of Kepler's laws is just that the planets travel in an ellipse. Second law is the speed of the planet, which we discussed before, that the planet sweeps out, as they like to say, the same area in the same time. So if we look at these three areas, and I showed this in the first video as well, just showing it again, that these purple areas are the same exact size. So if these were slices of pizza, everybody would be getting, all three people getting exactly the same size pizza. Some are skinnier and longer than others, but they're actually the same exact area, same size. And so somehow Kepler comes up with this law that the planet will sweep out the same area in the same time. Consequently, it's moving much faster. Look how far it's moved. This planet has moved when it's close to the sun. When it's opposite and far away, it's only moved that much in the same amount of time. So if it took 1 hour or 1 day, say it took 1 day to move from here to here, it also takes 1 day to move from here to here. That's why the sun in the ephemeris, or you're looking at your astrology charts, you'll see that the sun varies in speed from about 58 minutes or 57 minutes a day to 1 degree 1 minute a day. Why is that? Because when the sun is moving 1 degree 1 minute a day, it means that the Earth is near perihelion. The Earth is near its perihelion point. So that's why it varies. And the speed of the sun is actually the speed of the Earth. We feel like we're stationary even though we're moving. So the speed of the sun in your geocentric chart is the same as the speed of the Earth from the sun's point of view. So now you know why the speed changes. And the fact that the speed of the sun, or what we call the apparent speed of the sun, it's actually the speed of the Earth, varies from about 57 minutes, a little bit less than 1 degree, to slightly over a degree. It's not a huge variation. Why is that variation not very much? Because the path of the Earth has low eccentricity. It's 0.02. The path of the Earth around the sun is close to being round. If it was perfectly round, zero eccentricity, then the speed of the sun would be exactly the same all the time. So, at least using Kepler's laws. We're going to get to phase 2 of this as another little thing to this, but based on what we understand right now. Okay, and if the Earth had a larger eccentricity, the daily speed of the sun would vary much more dramatically. Okay. All right, so that's Kepler's second law of motion. I don't think I need to read this word for word. I've covered all that. And the third law of motion has to do with how fast the planet is relative to how close it is to the sun. Now you know that Mercury is very close to the sun and it's traveling very fast. Heliocentrically, Mercury travels around the sun in only 88 days. Geocentrically, things look different. But the planets that are closer to the sun orbit around the sun faster. So you know that Mars is slower, and then Jupiter's much slower, Saturn even slower, Uranus slower, Neptune, Pluto extremely slow. Pluto takes a very, very, very long time to go around the sun, and it's very much farther away from the sun. There's an exact formula that determines how fast the planet goes based on how far away it is from the sun. And the formula is this. It's Kepler's third law of motion. The square of the orbital period of the planet is directly proportional to the cube of the semi-major axis. This is so weird. I mean weird in that, like, whoa, really? Why would this proportion exist is, perplexing, but it does. If you take the semi-major axis, that's this A, halfway from the center of the orbit to the end, and you square it, like suppose it's 1,000 miles. So you square 1,000 times 1,000 is 1,000,000. Well, the square of this distance is proportionate to the, let me see, the square of the period is to the cube. I'm sorry, you cube this distance. So if this was 100, if this was 1,000 miles, it would be 1,000 times 1,000, which is 1,000,000, times another 1,000 is like whatever it is, like some crazy big number. I think it's 1 billion or something. Yeah, it'd be 1 billion. You cube it, you multiply it by itself 3 times, and that's going to be proportionate to the square of the orbital period. Orbital period for the Earth is 1 year. So the larger the semi-major axis is, the farther away the planet is, the slower it is. And because it's the cube of the semi-major axis to the square of the speed, how long it takes the planet to go around the sun, which is its speed, what this means is Kepler's, I'll read from this quote from nasa.gov, Kepler's third law implies that the period for a planet to orbit the sun increases rapidly with the radius of its orbit, because it's being tripled, or not tripled, it's being cubed, multiplied by itself 3 times as the distance is doubled. So the speed at which the planet is going is getting much slower with say a moderate increase in the distance. It gets way slower. That's why the outer planets are extremely slow compared to the inner planets. Thus we find that Mercury, the innermost planet, takes only 88 days to orbit the sun. The Earth takes 365. The Saturn requires over 10,000 days. Though Kepler hadn't known about gravitation when he came up with the 3 laws, they were instrumental in Isaac Newton deriving his theory of universal gravitation. So Kepler makes these discoveries. Really extraordinary how the heck he figures this out. But he figures out that these formulas work. And then because they work, other people come along later. Newton comes, about 100 years or more after Kepler. And he develops these laws of gravitation building upon Kepler's discoveries. You know what? I need to look up. I know when Kepler lived. Let's look up Isaac Newton. You can't see what I'm typing, but let me just type this in. When did Newton live? He lived, Sir Isaac Newton. I just don't want to say something. So born in 1643. He lived in the late 1600s. So actually, he's only about 75 years. He dies in 1727. So that is close to 100 years, because Kepler died around 1630. Newton lived a lot, almost 100 years. Anyway, 75 to 100 years later, and not important. I got a little sidetracked there. So anyway, Newton comes along later, 75 to 100 years later, and figures out some more things, laws of gravitation, and part of his ability to do that was to be built upon what Kepler had discovered. Excuse me. So Kepler and his theories were crucial in the better understanding of our solar system dynamics and as a springboard to newer theories that more accurately approximate our planetary orbits. Okay, I think that's it. Yeah, just some conclusions about Kepler's laws of motion. These laws are a mathematical model. This is important. They're a mathematical model that describes where a planet is located. There is not a cause in the sense of some force or reason for why the formula works. When Kepler discovered these laws of motion, I don't know why it is, but a lot of people are under this belief that science is about causes. Physics usually has nothing to do with causes. Depending on what you mean by cause, it has more to do with a mathematical model that you make this formula and the formula works. There's no cause, like we don't know why the formula works. As we learn more, as scientists learn more, they do learn more about, you might say, causes, reasons foundations. But most of physics is better thought of as mathematical models. And what we mean by that is you have a formula, excuse me, you put some data into the formula. In this case, you take the 6 orbital elements, you stick them in these formulas, and presto, out comes the position. So it's just that there's, for some reason, mathematical formulas underlying nature. That's a better way to think about what astrophysics, like the physics of, the formulas for astronomy. So I'm just trying to clear away some confusions. I mentioned in the earlier videos in this series that some people think that looking up planets in an ephemeris has somehow given you some deep insight into planetary motion. All it's done maybe is reinforce your understanding of the speed of planets just by looking at them all the time and how most planets go retrograde, etc. But it has not given you any better understanding of how the positions are determined, which is what I've shown you. They're determined through Kepler's laws, which we've now gone over what they are, and they are applied to the orbital elements, and out comes the result. If you were in college in astrophysics, from here you would then go on and practice getting the data, sticking it in the formula, and actually doing it more often. But at this point, you understand what the astrophysicist is doing. Excuse me. You understand the concepts behind what's done. So anyway, getting back to Kepler, a little bit about him. In 1609, he published the book Astronomia Nova, delineating his discoveries, which are now called Kepler's first 2 laws of motion. And what is just as important about this work, to quote from another source, it is the first published account wherein a scientist documents how he coped with the multitude of imperfect data to forge a theory of surpassing accuracy. And a fundamental law of nature. Today we call this the scientific method. So these scientists are saying it is the first published account of science, of the scientific method, of looking at observations and getting increased accuracy by taking all the complexity into account, refining it, and validating through observation with a clear formula, and that is validated through observation. In 1612, Lutherans were forced out of Prague, so Kepler moved on to Linz. So he was in Prague for a while where he made his discoveries, working in the observatory for Tycho Brahe. His wife and 2 sons had recently died. He remarried happily, but had many personal and financial troubles. 2 infant daughters died, and Kepler had to return to Württemberg, where he successfully defended his mother against charges of witchcraft. His mother practiced herbalism and what the Catholic Church considered to be witchcraft, and he went and defended her and got her from going into jail. I believe he succeeded in that. And then in 1619, so this is 10 years after he published the first 2 laws in the previous book, he publishes Harmonices Mundi. I'm probably destroying the proper pronunciation, and he describes what is now being called his 3rd law. So anyway, that's a little bit of the history behind this. Okay, my friends, in the next video, we're going to learn about how planetary positions are determined more precisely. Kepler's laws of planetary motion get the positions pretty darn accurate, usually within, I think, about a half a degree or so, depending on the planet and the situation. But to get them more precise, we have to take into account what are called perturbations. And perturbations are something that astronomers have wrestled with especially the 1900s and even into the 2000s, but a long time there of wrestling with perturbations to master how they work. Really kind of tricky stuff, but the principle behind it is simple. And it's this issue of perturbations that has to do with the mean node and true node and understanding how they're calculated, and then some additional information of an analyzing to show that the true nodes really are true. So let's learn about perturbations in the next video. Probably take maybe at least 2 more videos, and then to also cover how we determine that the true node really is true. And there we get to something very important to astrologers, and also that's been a bit controversial. Do you use the mean node? Do you use the true node? Are either one of them really true? And I'm going to make a sort of a radical, strong statement here. The true node is true. And what we've learned so far is going to help us in following this additional information that demonstrates what I think is a clear, makes it very clear that the true node really is where the node is. So it's one of the benefits of understanding all this is to determine issues like this. Okay, my friends, I will see you in the next video. God bless. Namaste.